represented in terms of n, and c is your coefficient which is multiplied, we can say that f of n has a complexity of O of n, right? Okay. What about 2n plus 3, which is less than or equal to 7n? Again, f1n equal to O of n. True? So, what about another, and this is your function f of n, and this is c multiplied by g of n, which is less than or equal to, then we say the complexity is in terms of n, O of n. One more way of doing is 2n plus 3, and then we can also say 2n plus 3n, which is less than or equal to 5n. Again, for n is greater than 1, it again comes to this complexity f of n. What about, okay, so what about this case, 2n squared plus 3n squared? So we can say that this term and both of these terms we can represent by multiplying them with n to get the complexity. So what about the squared term? 2n plus 3 is less than or equal to 2n squared plus 3n squared, where n is greater than or equal to 1. This becomes 5. Two plus 5, again 2 plus 3 becomes 5. So this is also true. So complexity of this side of g of n becomes O n squared. So complexity is f of n of this function is f of n, and of this function is O n squared. So can we say that f of n is equal to O n? Then this f of n again has a complexity if we take this statement true, and then we have f of n O n squared. Is it correct? Yes, it is also true. So f of n essentially belongs to which class? This class of algorithm. Okay. f of n belongs to this class of algorithm, and your n squared belongs to this class. So all algorithms above this n, they are referred to as the upper bound class functions. So all of these functions, n squared and cube polynomial function, they all belong to the upper bound. So this function f of n, which is given by 2n plus 3, will always be true for all functions which are greater than n. They all be true, but are they useful? So in order to measure the usefulness or consider the usefulness, we consider the least upper bound value. So in this case, the least upper bound value that we have here is not n squared, n cube, or polynomial n raised to power n. It is f of n O n. So for this function, the upper bound is O of n, big O of n. So we can write this as O n. So we have come to the conclusion that yes, your f of n function, your f of n function in this case, in this example, was true for on squared, and functions that are in the upper bound. They are true but not useful. So we take the least class of function O of n as the big O of n as the upper bound. All the functions that are greater than n, they become the upper bound. So we take the least function for upper bound. So let's see for the case of if we take 2n plus 3 equal to log of n. Is it true? So O log of n, is it true? This does not hold. So this complexity does not hold. So all the functions that are below your n, they become the lower bound. And your n becomes strictly tight bound, or the theta. So all functions below your n, they become your lower bound. All functions above your n become your upper bound, and n lies on the tighter bound. So all bounds that are greater than your value n, they are true but they are not useful. So what about omega function? So the function f of n is equal to omega g of n function if and only if there exists a positive constant c and n naught by definition, such that your function f of n is now greater than. First we have to determine the lesser value. Now we are considering the higher value. If f of n is greater than some value, some coefficient, some constant multiplied your function, some coefficient multiplied your function g of n for all n greater than equal to n naught. So this determines if it is lower than this. If f of n is, some function is lower than this, we find the lower bound using your omega. C multiplied by, let's write it neatly a little bit. Your f of n should be, because we are trying to find the lower bound for a function, f of n should, we find a function that is lesser than this given function g of n for all n greater than equal to a fixed value n naught. Let's go to that example again. We are given the function 2n plus 3. So we have to find a function that gives us higher value than this function f of n. So what can we put here such that this term become higher? F of n becomes a higher value than this. So for example, we can put 1 n for all n is greater than equal to 1. So it holds true. So we have here c, which is 1, multiplied by n, which is g of n. So we start from n equal to n naught starts from 0 onwards. From 0 onwards to 1 greater than 1, we can say this holds true. So we can say your function is f of n is omega of n in terms of n. So can we write 2n plus 3 is greater than 1 into log of n, right? For all n greater than 1, yes. So we can say if omega of log of n. So this is also true. So what about if we test for n squared? So can this hold to n squared is greater than your, this value will be greater than n squared? For n is greater than equal to 1. So what about 3? If we put in 3, 6 plus 3 is 9, and here we have 9, so it does not hold true. So f of n, where omega of n squared, it does not hold true for all values of n is greater than 1. It does not hold true. So we are restricted towards the lower bound, less than your n, log of n, squared of root of n, then we have n log of n and 1. So these functions are in the lower bound. So any function in the range of lower bound is okay. Which is more useful? Which is closest or equal to the less than the theta value, which is your average, nearest to your average. So which is the nearest? n. So 2n plus 3, we can say the theta is n. For this function f of n, we can represent it like this. It is true for log of n, n log of n, or 1. It is true for all these values, but this one is closer to your theta or the average value. So we are going to consider this value as your big omega. So what about the theta that we say the average case? Let us now study the average case. Okay. The average case, or the theta that we have here, we can represent it by definition. Function f of n should be less than your 2n plus 3, and it should be it can be represented as this. So we are limited between this and this. We have to find our theta. So what is your theta value? So if we put 1 in the n is greater than or equal to 1, if we put n, if we consider theta n, it holds true. So 1 is less than 5, which is less than or equal to 5, so it holds true. However, if we consider square term which is greater than 1, so let's see square term 3, if we consider theta n squared, let us see that 9 is less than equal to 9 less than equal to, what about 4? So this does not hold true for squared term for n is greater than or equal to 1. So we fail at this O(n) squared, where theta n squared, in case of theta n, it holds true. Similar is the case if we check with log of n, it will also fail. So the most tighter bound that we have here is theta of n for this function O(n plus 3. An example function is this. Example function is this. So for this theta that we have determined, O(n) is the average case. For all other functions, n squared or log n, either going towards the upper bound or log of n, n log of n, these terms, or be going towards n squared, n cube, and polynomial values. Either we go towards your upper bound or lower bound, it does not hold true. But in the case of n, this class of function is satisfying this theta value for this function. So the average case for this function f of n, your theta belongs to the class of theta n. So asymptotic notations should not be used for best case or worst case analysis. They simply estimate the complexity of your time complexity of your function, given function. So we have to keep this in mind. So a revision of the topic we have discussed and written in theoretics.